we go. All right. Just to lead off, like I was mentioning earlier, if my internet does have any issues, please let me know so I can re-clarify anything you may have missed. So let's start with my presentation. So on my side of the thesis, I focus more on the implementation aspects or practical application aspects of using an artificial intelligence machine learning algorithm for automated vulnerability type of analysis. And then Eric's presentation after me will focus more on the algorithmic details itself. All right, so we will dive in here. All right, just a brief overview of the presentation, especially if these slides get emailed out later. Hopefully I can keep it under 20 minutes for you guys. As a brief overview, again, our topic is using the artificial intelligence machine learning algorithms in more of a real world practical aspect using actual programs rather than just theoretical models. And we're wondering if we can use these actual programs to do the validation of the algorithms or not. And this is very important because it expands the opportunities for pen testing teams or blue teams and other cybersecurity professionals to have more time on their hands to pursue more complicated assessments in other cases or patches, whatever have by skipping kind of the menial, simpler, vulnerability type of assessments. So we did conduct a literature review before we went into the actual implementation portion of our project. So to start off, I'll butcher this name, works by Sarate. In 2011, he published a paper that used probabilistic algorithms instead of your traditional Markov decision process or other machine learning type of algorithm. And his algorithm was able to handle a large scale type enterprise network, a simulated one, of course, and was entirely based around sets of probabilities. And he built this using IDS, IPS detection, whether or not they to risk using a 0-day and having it no longer work in an actual environment, and how traceable an attack was back to the point of origin as the risks, essentially, whether or not they wanted to take particular actions on the network. In 2012, he moved on to more traditional model using the partially observable Markov decision process. And this model was more so able to handle uncertainties in the virtual network that they were attempting to model. But due to the nature of how POEM-DPs tend to work, it was restricted in terms of network size due to the computational difficulty of the algorithm in itself. They had to devise a method of splitting up the network into different chunks. So they had a custom algorithm which did that for them. Moving on to a different work, this one used more of a contingency problem type of basis instead of pure probability like you have in a POEM-DP model. So every action would essentially have an else statement whether or not the action could perform. So it's very per se, and all of these were laid out in a tree of possible actions rather than a grid of states or kind of a transition matrix of different states you could move through. And that was fairly neat because it allowed for actions to, like, again, have very specific criteria whether or not they'd work within a network, and it was able to account for facts where you could keep going down this rabbit hole of a particular action, but it may not pan out at the end. So they had dead end nodes to allow the algorithm to restart and attempt a different path. Similarly, there was, again, computational problems with using such a large network. So it had an algorithm similar to Sarate's in 2012, which divided up the network into smaller bite-sized chunks. And then finally, using kind of reinforcement learning. This is an interesting approach in machine learning. It does use existing MDP or POEM-DP models, so it doesn't require the entire rewrite of existing model, if you just want to add reinforcement learning to it, is very compatible with these existing models. Because the majority of what it does is essentially rerunning the model over and over again in order to view different outcomes of different options it can take. So it's good for being able to assess something for long-term like applicability, and it allows you to kind of scale over a greater duration of time rather than just a single simulation. Of course, this compounds kind of the computational problems, so optimizations to the underlying kind of framework need to be conducted via pruning or tree search, which I won't go into in depth. Let's move on to kind of our background of what our thoughts were.
Connor,
yeah.
I have one question. So when you say this, the last one is a reinforcement learning.
Mm-hmm.
So that is different from the neural networks reinforcement learning, right?
Right. It's they're kind of similar in how they work, because the reinforcement learning like this is, like I said, just a kind of rerunning of the existing models in order to account for if I take a certain action in this model, does it cut off a future opportunity for me? And that wouldn't be visible to a traditional POEM-DP model. Whereas
so
by
when
running
you do the rerun means that you need to adjust the parameters or anything to make this better compared to the previous running?
Yeah, right.
Okay, so what kind of parameters you need to adjust, do you know?
It'd be, we didn't delve into a ton for our particular problem, but it'd be more so parameters like around essentially like what paths you would take, or like what risks, if you encoded such as like a discoverability risk into this type of problem. If you were to take a riskier approach, would it yield a better long-term outcome over, say, 100 iterations than if you took a safer approach?
Another point about reinforcement learning would be that, like, if you're using an approach kind of like what he said with like pruning or tree search, where you're making simulations and stuff, you'd simulate you'd make different simulations or sample from a different set of simulations, like each time you restart the next, like each epoch, basically.
Mm-hmm. I see. Yeah, go ahead.
Okay. So going into more of our background for how we envision our implementation working. Again, just in case you had no idea what I was talking about in the previous lit review section on MDPs, our POEM-DPs. An MDP is a machine learning kind of algorithm using a set of possible states and actions. Each action can lead to, with a certain probability, a different state. And there's functions that yield a certain reward or punishment from this. And mathematically, it's defined as a 4-tuple. As far as POEM-DP goes, it's very similar to the MDP-based model, except the agent is entirely based on observations. It does not necessarily have an exact grasp of what state or what actions it may be available to it in kind of its virtual world. Everything is driven by observations and what it believes to be the correct state that it's in. So it's a certain probability of whether or not it thinks it's in that state. And that's a more complex mathematical model defined by a 7-tuple. And Eric will go delve more into the differences between stuff like that and how Markov decision processes work in his portion of the presentation. So here's a kind of use case diagram we've envisioned for an implementation like ours. So of course you'd have on one side of the model your pen testing and blue teams, who would be the users of this actual application. In an existing enterprise environment, we'd hope that there would be existing infrastructure like Nessus or another scanning framework to provide network information from your kind of end user workstations and servers. So our particular algorithm would integrate with a solution like this to pull down network information and then generate vulnerability reports that could be useful to pen testing teams and blue teams, kind of speed up the vulnerability discovery process for them, and skip some of the nitty-gritty details. And then the further extension of that would be to do automated adversary functions, which would take those vulnerabilities that were discovered on the network and implement them against your target systems to kind of prove a vulnerability to your blue team or your pen testing team.
So, Connor,
Mhm.
generally speaking, so when you do the penetration testing, you need to set up a kind of like a conditions, right? So, what kind of time and duration and what date? So, what services you want to do a test? So,
Right,
you need to get all this information into the system in order to
right,
send a certain kind of like a get off jail letter with a system you want to test, right?
right.
So from that ends, do we have any consideration for this work?
Well, at least how the system works at the current point in time is it would be controlled by the pen testing team or blue team. So if they wanted to conduct the tests, of course, they'd have to follow their usual kind of protocols, like you said, scheduling which services they want to target, when they want to do it, and all the kind of get out of jail free cards, like you mentioned, in case they get into a system and kind of wreak havoc, I'd say. So that's all still under the domain of the pen testing team. It's not something that just would run willy-nilly by itself.
Yeah, so yeah, in addition to that, you also need to think about the recovery plan, right? So after you deploy the test and how you recover the system into the original states. So this could be another issue, you know, so
Well,
if you use the automated tools.
When I talk about Caldera, I'll kind of go into that a bit more, but there is, because that's the MITRE tool that we're using that incorporates some automated cleanup routines to help recover these systems back to their original state after a test.
Okay, so do we have the that system set up in our current demo or prototype?
Yeah, it's native to Caldera, so it works automatically without any changes by us. That's something that existed already.
Okay, gotcha.
All right, so dig into just kind of Nessus here for a bit. So this is our choice for a kind of network scanning tool. It's fairly common in the cybersecurity industry as a vulnerability scanner on a network. So semi-automated type of system. So you schedule scans and configure very robustly like what you want to scan in particular, OS or services, like you mentioned. If you just want to look at something at a particular date and time, it's all definable within the Nessus interface. And I would assume most major organizations that are doing kind of regular vulnerability assessments like this are using some sort of scanning framework that runs on a scheduled basis. So integrating something like this would provide a good source of data where you don't necessarily have to run your scan exactly before you deploy this tool. You could use previous scan data. And in that regard, Nessus is able to export in its .nessus format, which is XML, CSV, PDF, HTML, database files. So if you did end up using a different kind of POEMDP implementation or a different language to implement that, you have a variety of data sources at your hands that you could conduct this with. And it also provides a very clear-cut kind of risk score for each node. So if you wanted to kind of base your rewards off of how risky a vulnerability is, it's easy to do with a Nessus type report. And then to go into Caldera, it may not be as well known as Nessus because it is a relatively new tool by MITRE that's still under active development. So it's kind of in its alpha beta stages at the moment. It's completely open source, and it is a way of emulating adversaries against your network. So if you had, say, your common APTs and you wanted to test them and see if your signatures or whatever detection utilities on your network could pick them up, Caldera would be the type of software to be able to do that without having to have a person sitting on the other end conducting the attack. So it can take details and facts about a target network, and it does this as it runs even, so it can gather additional information as it conducts an attack and incorporates that into further or future attacks and run a predefined set of vulnerabilities against it. These are all stored in a library based on the kind of MITRE attack framework, so they're all categorized by what they do or what stage of attack they're used in. They're identified by unique UUID values, which lets them be easily looked up by like a program like ours. So if you want to target and use a specific vulnerability, all you need to know is a UUID value associated with it. And it's neat for its uses for like red team and blue team, as with the red team based side of Caldera, once you exploit a system automatically, if you wish to further dig into it, it has the ability to use a reverse shell as part of its kind of native, its agent that it deploys onto machines it infects per se, which is called Sandcat, and you can use that as kind of your entry point instead of having to find another way around. And it also generates artificial normal internet traffic. So if you have a defined set of behaviors for an organization, you can have it hide itself within like a stream, say, of like a Zoom, like call emails and regular system updates or services that are used. And then as far as blue team goes, like I mentioned, you can have these predefined adversaries, either one that could be generated like by a program like ours, or like an APT style group that you came up with, or you can play what an actual person may do against your network or a particular hacking style. As far as the methodology for our implementation, so our system is developed using both Python 2.7 and Python 3.6 plus, primarily using the PyMDP toolbox and POMDP for the algorithm. And you can see kind of on our system architecture diagram over here, we have it all consolidated onto one node. Of course, in an actual enterprise environment, you can break out your Nessus scanners into dedicated like scanning nodes or specific items that you use for scanning in order to allocate more processing power to that, especially on your larger enterprise networks. And Caldera also has the same capability. You can run it on remote hosts if you want to give it a bit more oomph during its automated attack. And that would be perfectly compatible with our type of system, since both Nessus and Caldera kind of have a central control point of software that you could just link up your remote nodes to. So it wouldn't be a particular concern for our type of deployment. And then everything else is, of course, connected to your kind of corporate network, which in our case will be 3 VMs, and our attacker VM, which will let us see what the algorithm is doing and control Nessus, Caldera, and all that usual stuff. One thing to note is for whatever VM, if you do run Nessus, Caldera, and the algorithm on one VM, Nessus and Caldera and themselves are kind of resource intensive. So it's important to have a virtual machine with a newer version of Kali or another supported Linux release, and to give it a decent chunk of processing power and memory. I think the configuration we typically used was around 3 gigs of RAM with 2 decent processing cores, and that allowed Nessus and Caldera to be happy with their setup.
So, Connor, can you go back to the slides? So regarding to this automated pen testing block, do we have a flow procedure among those errors? I'm trying to understand what is a flow procedures.
Yeah, we do have that in a later slide.
Oh, okay.
So I'll go over the network environment a little bit real quick. So our testing environment is fairly simple. There's just 3 virtual machines running Metasploit 2.0, connected to kind of like essentially a switch along with our attacking computer. So it's not a complex network environment. They're all sitting there on the same subnet. And we use Metasploit 2.0 in order to provide kind of an easily configurable test case to run our algorithm against, since it does have very well-defined sets of vulnerabilities of what exactly it's vulnerable to, so we can perform a more accurate assessment of whether or not the algorithm is working. And then we have our, of course, primary attacker PC, which is running Nessus, Caldera, and the algorithm itself. So not a very complicated setup at all, but would be expandable in future works, of course. So the vulnerabilities that we were looking at in particular, just to kind of make things easy, was a FTP vulnerability. So the one built into Metasploitable that's one of the most notable was the VSTP 2.34 backdoor, which allows you to go to your kind of FTP login point or service and enter a smiley face as your username, which opens a backdoor. So fairly concise root access to the machine. As far as the SMTP side of things, it was a user enumeration vulnerability. So the SMTP server would happily return you a list of all the users that are active in the SMTP system, especially for an operating system like Metasploitable. It's a bad idea to return those since the passwords are generally weak. As far as SQL, it was a Postgres misconfiguration. So Postgres, if you did SQL injection with it or some other backdoor in the software, it would allow you to write directly to the Postgres directory itself, which from there you could overwrite the Postgres program files or any other type of exploit to replace those files if you're Trojan or whatever you'd want to do. And then the simplest and surprising, the highest CVS score was just using a VNC default password. So log into the two nodes that have that vulnerability, you simply use the password with VNC. And that's something that's picked up by Nessus. The thing to keep in note though is our algorithm, the POMDP PI package, required hard coding these vulnerabilities. I'll go into more of that a bit later. And again, all these are available through Metasploitable. So if you use Metasploit, you can do these exploits by hand if you wish to verify that they're working. So, and the manner in which we configure them is kind of present different attack services. So one was similar to like what a server would be. So you wouldn't have necessarily the workstation type services running on servers like FTP and SMTP be running on the server, as well as SQL. And then your workstations have VNC, say if you have people working from home, you want to log in. So kind of that kind of configuration regime to present some differences in the network for the algorithm with. And then here's that kind of system flow diagram for how the system itself works. I'll kind of step through that with our pointer here. I won't delve, of course, into how Nessus conducts its scans, because that's entirely in Tenable's kind of domain of how that works. But essentially, it's a plugin that would work against our network, provide kind of a detailed report. We export that report using the Nessus format, which is XML, and that gets parsed into the data for the POMDP algorithm. So that would be the equivalent of the reward matrix, which is based on the CVSS scores of the vulnerabilities, and the transition matrix, so what actual vulnerabilities are there for it to move against. That of course gets fed into the POMDP algorithm, which I will let Eric go more into an explanation of. But the gist of that is you get your per machine kind of policy of what exploits should take, which at the end is a network policy, so a policy of exploitation against the entire network, which you could then feed either, say if you wanted to give your pen testing or cyber blue team CVE for particular vulnerabilities that worked against the network, you could do a CVE lookup and generate a plain text report that'd be easily human readable, which would let them conduct their job. Or if you wanted to feed it to the automated kind of adversary framework, like I mentioned earlier, you could use the UUID lookups and have Caldera generate a plan of attack against the network. I kind of go into our results here. So I put in the Nessus scanning times because I figured they are important. So on our little 3-node network with the machine configured, as I mentioned, with like the 3 gigs of RAM, it took around 6 to 8 minutes on average to conduct a scan against the network. And that was with a cut down set of plugins. We only targeted the stuff that we knew we had running. We didn't want a bunch of overhead. And this is likely similar for what other enterprise environments have. So Nessus would be pre-configured with the targets it should scan, what it should scan for, and stuff like that. So it's not atypical to have it set up like that. But the important thing to know is scanning is necessary to use our POEMDP algorithm. You can't just run it by itself. And so you have to take into account the scanning times that it takes Nessus to complete. So if you have a massive enterprise network and you're trying to do an exploitation against that of hundreds or thousands of machines, Nessus could take quite some time to scan through all that. So if it's quicker to do whatever small vulnerability test that a pen testing team wanted to do, it's probably more viable to do that by hand, of course. And as of all things, the scanning time is dependent on the network and the scanning power available. So if you give it a more powerful node, maybe it wouldn't be as much of a consideration because it would have the ability to complete that much faster. All right, so the POEMDP itself did successfully navigate the replica network. And when I say replica network, it's because it is building its own model of the network based on the data that Nessus gives it. It is an offline planning only kind of solution, so there's no really updates coming back from the actual network on stuff it finds. It's all based on that kind of pre-scan data. And there's nothing coming back from Caldera or anything like that. So it's running its one run based on this model network that it generates from the Nessus data before giving us the report. All the exploits that it chose were ones that worked on each of the nodes. So it was successful in attacking the network per se. Some of the exploits weren't necessarily our first choice. I think some of them were just like particular like quirks of how the algorithm works. It wasn't a, but it wasn't a failing per se because all the exploits it did chose worked. And then the algorithm was able to complete running against a 3-node network in several minutes. And of course, this does depend on the granularity at which you want to approach the problem. So if you do want more accurate scans, you can run more epochs and more simulations per epoch, but that does take, can take quite a deal more of time. So it's just something to consider. As far as issues that we ran into at POEMDP, so I mentioned earlier the hard coding of the vulnerabilities. So the POEMDP package lacks the ability to dynamically add in essentially what your transitions are, because they're hard coded into the framework using actual code structures rather than say like a data file or a configuration file. So it's very hard to kind of generate code dynamically. Essentially is what you need to do in order to do this, and it wouldn't be as feasible with this infrastructure. So you have to spend the time to code in all the vulnerabilities you'd like to use of the algorithm into the program itself. It's not something that's just you can do on the fly. And Caldera is kind of the same way. You can do some automated generation of vulnerabilities with Caldera, but as you start to get to your more complicated exploits and stuff like that, you really need to go into it by hand and write your exploit file that Caldera uses, just like it would be essentially like what your Metasploit scripts would do. You have to take time to make sure it's performing correctly and targeting what you want and giving the results and is able to do the cleanup and stuff like that. So your 0 days cannot be immediately used. You have to spend the time and actually write the file up and prove that it works before you can deploy into a system like this. And so that limits the speed, of course, at which new exploits can be found and used. And then you need to spend the time customizing for every network. Not all networks are going to have the same vulnerabilities or have the same services that you wish to target. So you want to configure the algorithm to be more specific to your network. You don't want it looking for something that doesn't exist on your network, and you wouldn't want to waste the computational time that it takes Nessus to scan for your stuff on your network, stuff like that. So as far as the Caldera attack plan, so the POEMDP policy was able to be converted into a Caldera attack plan. You can kind of see a screenshot of what it looks like over there, because we did do simple exploits that would essentially grant you root access right after exploitation, so there was no need for really a multi-phased attack. And the simple file just kind of over here is an identifier that Caldera uses to track which particular plan it is. This is the plain text one that he would see when they ran it, and these are the 3 UIDs of the vulnerabilities that it would choose to run against the targets that were specified by the POEMDP. And it's not shown here, but there is another file that's also generated as part of like using the Nessus data and what the POEMDP determined was exploitable to kind of put rules on what Caldera can do, so it doesn't go outside of, say, the targeting systems that you wanted to try and exploit and attack your entire network. So that is generated as part of this automatic process as well. So kind of in conclusion here, using this kind of artificial intelligence machine learning method to find vulnerability in your network seems to be viable. And inherently good at finding patterns within a network. So if you did load it up with hundreds of vulnerabilities, it would take quite some time to run, but you have a pretty good idea of what would actually work and work fairly quickly. And our algorithm did pick out vulnerabilities that successfully worked against the target. So of course, the machine was purposely vulnerable, but we were able to validate that it picked the proper exploits for each machine. And of course, it's not perfect as a step forward. Like I mentioned, you can't use dynamic vulnerabilities in it, and it does take quite some time to do scanning against a large network, and it would take quite some time to simulate against that large network as well. So that leads to great opportunities to expand it for future uses. So if you wanted to be able to use it against more complex networks, say ones that have different subnets even, or different firewall rules that need to be taken into account, an algorithm like this could be expanded to accommodate for those, and future work on optimizations for AI ML type algorithms would go into play here and allow you to do these more complicated networks, as well as potentially swapping out and using a different POEMDP package and implementing the algorithm using that instead of POEMDP Pi would allow you to use more dynamic exploit usage, or finding another method of adding these exploits into the model would allow you to say, hey, run a scan against this network, and you may not know that you have a vulnerability there, but a model that can dynamically add vulnerabilities would be able to find it likely. And that would be an interesting route to explore in a future work. All right, and that is all for me. I believe we're doing a combined Q&A at the end, so if there's nothing to add, I'll turn it over to Eric.
Actually, let's do in sequential manner. So like we can ask you questions first and then to Eric. Can you tell us how you define these action probabilities in your transition matrix? So like suppose you are at stage S0 where you have a user privilege on a machine and you want to go to state S1 where you have like root privilege on this machine. So the actions that you will take to go from state S0 to S1, how do you encode them in your transition matrix? Like, how do you come up with these probabilities?
I believe we use kind of like the CVSS data on like how vulnerable a machine was to do that, but I think I'd have to ask Eric to answer that question a bit better since he spent the majority of the time in.
It looks like we lost Connor. You pretty much got it right though. So basically just took CVSS data, and that was how we kind of determined that.
Yeah, so yeah. And then
did you hear anything of what I said?
No, can you please repeat?
I believe for our model, we ended up using kind of like the CVSS data on to determine like how vulnerable the machine would be to it, but I'd have to probably divert to Eric to answer more of that question since he spent most of the time adjusting the model.
And the next question is that how do you make sure your actions are granular enough? Like in actual penetration test, you cannot just say like, hey, exploit 1 or exploit 2 or basically elevate privileges. You have to go in a more granular manner, like compose some kind of payload that you send to a particular application, then you get back, say, like a reflected cross-site scripting vulnerability. So then you know that the vulnerability exists. So how do you make sure your states and actions are more granular? Or like if you are to improve your system, how will you make it granular enough to be useful in context of actual, say, application penetration test?
Well, a lot of the initial data, of course, comes from Nessus. And I believe Nessus and the variety of plugins that it has does some of that kind of probing and testing off the bat in order to give you an assessment on what's vulnerable or not. And then passing that along to something like Caldera after the algorithm runs. Caldera natively kind of probes against the system and sees what works and what doesn't and takes note of that. So it does record for like further phases in the exploitation, what works and what doesn't against a particular node. And so that helps with the granularity some there. And then in future works, what would be interesting to do would be to take data like that off of Caldera, say, come back report like what failed and what didn't work against the node, and then rerun the POEMDP algorithm based on that Caldera data. But we didn't approach that in our particular model. But that would be something that would be possible and be interesting to conduct in the future.
If I can jump in, just to kind of add to that, like I think what, like what Connor said, you're right. I think Caldera really handles a lot of the actual exploitation part of it. And encoding vulnerabilities as atomic actions was more just like a choice for like practicality because we weren't sure exactly how it was going to work. Now I think that, it does work. We could encode compound vulnerabilities that require multiple actions and could move from state to state. But we chose not to, just for, for the sake of making sure it worked.
Okay. Anyone from audience has any questions for Connor?
I have one architecture question.
Mm-hmm.
So for the Caldera you implemented, so it's a single node system or it's a multi-agent system. How you want to, for example, if I want to coordinate the actions from multiple different network points, would that be available?
Yeah, so how Caldera is written is a neat piece of software. So if you start from a single point or if you start from multiple points, it's all configurable. Like when you launch Caldera and deploy its agents, its Sandcat agents. Mm-hmm. So you can have kind of what would essentially be a command and control node that coordinates your actions across networks. And it can, as its agents spread laterally or move laterally across the network, they all report back to the central node. And they remain on the systems until you tell them to delete themselves. So if you wanted to do a further exploitation from kind of a multi-network angle, you can then target specific networks as defined by, like, say, an IP subrange that the agents are on with a specific set of vulnerabilities, and then target a different adversary plan against a separate network or a different subnet. So it's interesting how it can coordinate. You can run multiple attacks at the same time as well with different attack plans. It really just depends on the computational power of the machine you're running it on and the characteristics of the network environment.
I see. So in order to incorporate with the machine learning modules, then what is the API available in the Caldera allow you to perform decision making and like a risk analysis? So are there like APIs available over there?
So the APIs are kind of funny because, like I mentioned, it is alpha and kind of beta stages. So the APIs were working a few versions ago, and I think they're broken currently, and they're working on fixing them. But the code is there for Caldera to be able to report out. Like I said, like, hey, these vulnerabilities don't work. Or, hey, this agent got deleted off the system, like an automated system deleted the agent, I can't contact it anymore, and then feed that back to the AI. Just be a matter of performing some like translation of what Caldera is able to report back to whatever framework the AI algorithm uses.
So for now, the API we're using Python, is that right?
Right, yeah. For now, we're using Python, and I can't remember if I mentioned it in my presentation. At the moment, what you can do programmatically is drop these kind of attack plans into the directories that Caldera expects them to be in, but a human does have to go in and start the actual exploitation. The API is currently broken that allows you to simply have a script start it for you. So until they fix that or figure out, because they're adding a bunch of new stuff, like the human generated traffic is very new, like less than 2 months old, and they're still figuring out how all that kind of meshes together. So as Caldera also becomes more developed, it will have a more standardized API that you could use.
I see. Okay, so any more questions?
No, I don't have any more questions. So
Yeah,
we can
so
move to
let's move on to Eric. So he will describe the ProMDP modules. So I checked the time. So we about spent more than 40 minutes.
Yeah, we went long.
No, it's good. It's good. You know, so for Eric, would you please control your presentation in about like a 25 or less number, less amount of time.
I'll do my best. I'll do my best to keep it short. Yeah, because I don't want to take up too much of your time today.
Okay.
Yeah, my
Okay.
apologies.
No problem. Yeah.
So I will do present. Can you guys see the slides?
Yeah, it's quite big.
Okay.
How can you shrink that to fit into the window size?
I mean, I could just do it like this. Is this okay?
So when you share, you can share the application. So maybe can you share the application instead of sharing the whole desktop?
Thought I was sharing the application. PowerPoint.
What I ended up doing too, if it's giving you trouble, is you go to slideshow and you could do presentation configuration. Just say you're browsing it as an individual and it opens in a window.
Okay. Right. So we're going to get to my half of the thesis presentation now, which is largely the same thing, but I talk a bit more about the implementation for the algorithm itself and kind of those details, and less of the configuration validation type stuff. So in terms of agenda, I'm going to give a quick overview. I'm going to give a quick overview of kind of like the state of the literature and stuff. I'm going to try not to repeat too much of what Connor already told you about. Just kind of the problem space in general. Let me give a bit of background on the technology we're using, the algorithm and everything, and kind of why we made the decisions we did. I'm going to talk a bit about the experiment and like the setup, the implementation details, that kind of stuff, and the results, and then talk a bit about kind of what we got out of it, what directions we can go in, that kind of thing. So I apologize, this will hurt your eyes. That's just kind of it's a section slide, sorry. So attack automation is really like a growing field within cybersecurity. I would say there's a lot of what I would characterize as low-level automation and that kind of thing that's already been done with vulnerability scanning, SIEMs, that kind of thing. You also have stuff like Metasploit, which for the rest of us on the call, I'm not sure if you guys are all familiar. Metasploit is basically a database of exploits to use for attacking computers. And so it's kind of a step above like low-level automation, but it's still a tool. It's a tool. It doesn't have decision making. It requires somebody to use it, and more importantly, use it well. Vulnerability scanning is really kind of the only strong focus for automation at the moment. Like I said, SIEM, security solutions, all that stuff. Like from the security side of things, the defense side of things really is where all the focus is right now. And pen testing as a whole is still a very human, labor-intensive process, because it kind of requires a human mind to plan and make decisions, at least for now. The problem with this is really uncertainty, because most planning algorithms, most algorithms in general, don't deal with uncertainty well. A lot of, I'm going to kind of lump these together. This isn't an exhaustive list, but there's kind of 3 problems generally with planning algorithms, which the first one would be that they require a priori knowledge of the environment in order to run successfully. They have to know everything about the environment they're in, which when you control the environment they're in, that's great, but that's not really possible in a network scenario. Another problem they have sometimes with more like traditional machine learning, like neural networks and deep neural networks kind of stuff, is training data bias. They rely on a baseline of previous learning, and sometimes, you know, there's flaws and issues with that. And then the third one would be that they just can't handle all the data involved when trying to make decisions, trying to represent all the possibilities. We'll talk a little bit more about that in a minute, but the algorithm we chose manages to avoid those first 2 difficulties, and it has mitigations for dealing with like the huge amount of data involved for dealing with network scenarios. Like I mentioned, networks are really kind of the big problem point. They're super dynamic, lots of detail, lots of information, and simulating networks is really the hard part of automating this, because a lot of the tests have revolved around simulating networks, and it doesn't really work out for realistic work, because you either lose a lot of detail in the pursuit of speed, or it's just not fast. And losing detail is obviously not good, because then you're getting an unrealistic picture of the network. And because of the dynamic nature of networks, you have to be able to gather more information. You can't just say, hey, like, here's a picture. You know, here's a picture of a field 2 years ago. Now I want to know what that field is like today. That doesn't work. And that's the same thing with networks. You have to be able to gather new information. Another kind of focus, it's still very theoretical for what you'll shortly see are obvious reasons, but the idea of cognitive modeling, excuse me, the idea of cognitive modeling has really taken off in the field. The idea of simulating humans in order to make decisions instead of using more traditional algorithms. The idea being that humans are more adaptable, and especially if you're simulating like industry experts, like blue team experts or professional pen testers, then you're going to be kind of turning their knowledge and their capabilities into something a computer can make use of. An obvious problem with this is that right now it's impossible. If you could put a human in a computer, we would all be androids by now. So that's not really a thing yet. It's all very theoretical. Another issue is bias and kind of human flaws, because if you're going to make a cognitive model of someone, it's going to include their biases and flaws, and everybody has those. So that's kind of something that needs to be considered when doing research and stuff like this. But again, this is all very theoretical still. Gonna save your eyes the trouble. We're gonna talk a bit about the background now, kind of just help you understand the algorithm a little better and kind of what it really boils down to. We did choose to use a stateful representation and a stateful algorithm for this, which suffers from a pretty serious problem with an awesome name called the state space explosion, which basically what the state space explosion is that as you add detail to a stateful system, like a stateful model of a system, you increase the number of states exponentially. So say you're modeling a network of 3 computers and they each have 3 pieces of information. That means that in order to model that network, you're going to have 27 total states in order to hold all the different combinations of all the different features. Let's say you want to add a fourth feature because you like having slightly more data. When you do that, the number of states jumps to 81. So you get exponential growth as you add information or states to your system. So it's a big problem. It's a big limitation of stateful systems, but there's some mitigations we can do for that, which we'll talk about in a bit. Another problem with a lot of stateful systems is how do you get information into the system? Because they have that a priori problem where they need to have all the information available and they can't deal with uncertainty well. We'll talk a little bit more about that, but it's not a problem with the implementation we chose. What we're going to do is we're going to kind of start small and work our way up with these stateful algorithms. So this, if you've taken an AI or an ML class, or you've done kind of some work in this area, you probably know what a Markov chain is. It's a very simple kind of stateful automaton. And it's really dependent on something called the Markov property, which basically means that you only need the current state in order to determine the next state. So let's take this example here. We've got two states, S0 and S1. All you need, if you're in S0, say, all you need to determine what state you're in during the next time interval after the next time step is what you already have given S0. So you have transition properties, which are shown here. So if you're in S0, the probability that you will be in S0 at the next time step is 0.4. The probability that you'll be in S1 at the next time step is 0.6. These transition probabilities they're not going anywhere, so they are a pretty big feature of this stuff. But the important thing is that you only need the current state to determine the next state. Moving up, we're gonna add a couple things, and now the algorithm is called the Markov decision process, MDP. You heard Connor talk a whole bunch about that. This introduces the concept of action and reward. So like Connor mentioned, it's a for tuple. You have the state space, which contains all the possible states that the system can be in, because this algorithm does require a priori knowledge. So you have to know all the possible states. You have to be able to enumerate all the possible states. You also have a list of actions you can take in any given state. You also have a list of rewards for different state action combos. So the way transitions work in an MDP is that it's not, you only need the state, but you can choose any number of actions from that state, and that tells you where you're going to go. It's not just kind of random probability. So if you have a state and an action, you'll have a transition function or table, which will map your state and your action, and it'll tell you, you can do lookup in the table and say, for state 1 and I want to do action 0, what state am I going to end up in? And the table will tell you, oh, you're in state 3 now. In a similar manner, you also have a reward function or table, which maps in the exact same way. And what it'll do is it'll tell you for that transition what your reward is. So the idea behind kind of solving an MDP is to maximize reward, like a whole lot of other AI.
Is your question, is your reward always positive value? So suppose you are exploiting a cross-site scripting vulnerability, but you end up spending like 10 hours trying to exploit that. So how do you encode that part in your reward matrix?
So you can have negative rewards. You can have actions that are discouraged. You can have like an illegal move penalty per se. Or the way you can also do it is if you're using reinforcement learning like we did, you can also have a discount factor. So with the passage of time, the reward goes down. So like you said, if you're spending 10 hours on a vulnerability, then it's possible that there was another vulnerability you could have done in half that time or a quarter of that time. So the reward can be made to go down over time. Does that kind of answer what you were asking?
Yes.
Okay. So yeah, the goal is to maximize the reward, like a whole lot of machine learning and AI algorithms. I just have kind of an example transition here. It's kind of hard to visualize this, so I did my best. You have two states, which are both in the state space. They have to be, because that's how these are defined. You have an action, which is in the action space, because again, that's how it's defined. And so you're in the first state, you choose an action, and then that state and action pair becomes a transition. And when you do that transition lookup, it tells you what it tells. This tells you, sorry, I forgot about the laser pointer. This, based on this and this, you get the transition, and it tells you what state you're going to end up in. So, and then you get a reward, but I couldn't figure out a good way to visualize that, so I left that out. So moving upwards then from an MDP, we now have a partially observable Markov decision process, which introduces two key concepts that really kind of change the game and make this more usable and feasible in this kind of environment. These are observations and belief states, which I'll explain more in a second. Traditional MDPs are what you would call fully observable, which, like I said so many times now, means that you have to know the full environment. You have to know everything about the environment that it's happening in. It has full observability. You can see everything. There's no uncertainty. So a partially observable MDP, or a POMDP as I'm going to be referring to it, does not require that. And what it does is you make observations in order to gain more information about the environment, and then you have a belief state, which is kind of like drives your decision making. And when you make a new observation, you go ahead.
Yeah, so what does this belief state mean in context of security? Like, are you uncertain about existence of a certain vulnerability?
So the belief state in context of security. So the belief state really is just like it's more of what the algorithm knows about the environment than anything. And it can make decisions based on what it knows. It's not, let's see, let me try and restate that. So in terms of security, if you make an observation, you scan a computer that you're targeting. If you don't know anything about it, then you can't take an action maybe other than scan it. But if you make an observation of that computer and you learn that, oh, it has these vulnerabilities, based on what I know about these vulnerabilities, I can then, prioritize my decision making. It's more of just like kind of a current knowledge repository than anything, I think, is the best way to kind of think about it. Does that answer your question?
Okay, yeah.
Okay. So yeah, so that's observations and belief states. That actually was going to be my next thing I explain anyway. So compared to an MDP, there's a complexity trade-off, which, you're adding more stuff. It's more complicated, kind of to be expected, but it's just worth noting. Now, for example, I'm just going to run through like a POMDP update so you get kind of the idea of how it progresses and how it thinks, really. So part of the 7 tuple that defines a POMDP is the initial belief state. It's ground zero. It's what you think. It's what the algorithm thinks when it's born, basically, and that's where you start. So then, based on that, you'll take an action. The algorithm will take an action, and a transition will happen based on state and action, and you will end up in a new state. After that, the algorithm will make an observation based on the new state it's in to learn more about the environment. The belief state will be updated with that information, and then now you have a new belief state, and so you will decide on a new action, and then the cycle continues. So this will happen until you reach a terminal state, and Yeah, so that's basically how POMDPs operate.
So
Now to talk a little bit more about the, go ahead.
What would be your terminal state when you encode it in terms of like the security vulnerabilities?
So for this, the way I encoded it was basically there were nodes for each computer in the network. And the state basically was a list represented as kind of a list of those nodes, and that taken together was the state of the system. And based on like vulnerabilities and changes and stuff, if you don't know anything about a node, it doesn't say any, it doesn't give you any information about it. So you can make an observation about a node, you know, scanning a node, and then you will learn more about that node. So basically the way it's stored is it tells you the current state of the nodes in the system based on what you know.
Okay. Okay.
So, all right, so I'm going to continue then. Connor's talked kind of a lot about this stuff. We really tried to use open source technology where possible because we didn't want this to be something that was kind of boxed in and not reproducible. And kind of a happy coincidence that a lot of network security software that's open source ended up having Python support. Caldera had it. Nessus, we thought Nessus had it, but that's, I'll get to that in a second. And then obviously the framework. But the goal was kind of to take these separate pieces, take off the shelf stuff and put it together in kind of a novel way, not necessarily to reinvent the wheel or to, you know, write a brand new POMDP solver that nobody thought of before. So that was kind of the motivation behind it. As you heard, we use Nessus for the vulnerability scanner. We thought that it had a better Python API than it did, but for one reason or another, Tenable has decided to take a whole bunch of features out of Nessus's API. So that kind of sucked, but that was out of our hands. So not much we could do about it. And the POMDP solver we chose because it was written in Python, which we were already kind of leaning towards, and we said, hey, that's good. That will interface well with the other stuff we're doing. And because it's an open source solver and it's got a ton of customizability, it's got some cool algorithmic tricks, it seemed like a really good fit. And I would say that it is a really good and powerful tool. I'll talk a bit more about what I think about POMDP a little later. And then we chose Caldera, kind of same reason, it's open source. It's developed by MITRE. MITRE has a really good industry reputation. And then the Python integration stuff. It's also kind of the only piece of software I know of that does what it does with adversary emulation and that kind of thing. So I'm gonna run through a couple use cases, more or less Connor described. In terms of red team stuff, you basically, what a red team would use something like this for is to increase, you know, the attack surface that they're able to touch, you know, with permission, of course, because that's how that works. Or maybe to act as kind of a confusing agent, because with stuff like Caldera is, you know, human generated traffic, you can do things where, oh, a security team might say, oh, this computer on the network was just doing something shady and now it looks perfectly normal. That's where, oh, this one, and you know, you could kind of play whack-a-mole almost if you played your cards right. But basically the goal is to kind of increase the reach of red teams. For blue teams, kind of a similar idea, maybe that you could do more automated testing, that you could set up kind of a training simulator of sorts with something like this, where you can do more security testing and be a little less reliant on a human pen testing team. I'm not saying that this is necessarily going to replace people as pen testers ever. I don't know if that's possible, but I think it would be a useful tool for a blue or purple team to have. So I'm going to talk a bit about the experiment. The network setup we've already gone over in a lot of detail. This is kind of the network layout. Ignore attacker 1 and attacker 2. They're leftovers from previous attempts to make this work. We basically needed more processing power than those two could provide, so we ended up using attacker 3. But again, you've seen this already. This is not new information. So I'm going to talk a little bit about implementation work, though. Nessus, in both a good and bad way, did not require any implementation work because it didn't have Python support. So we weren't able to use that from the command line because Nessus's API is a lot less powerful than it used to be, which is unfortunate. So that has to be run. That has to be run from the web client, which is less than ideal. But again, nothing that can be done about it. For taking the input from Nessus and putting it into PomDPy, we did have to do a little bit of data translation and like XML parsing, but that's fairly straightforward. That was a Python script, and it wasn't very complicated. And then for getting the data, the policy that PomDPy generates to Caldera, that required a little more data translation, which again, nothing really complicated. But I'm going to talk a bit more about PomDPy though, because that was kind of the bulk of what I did. So like I mentioned earlier, it's very customizable and is arguably its biggest strength, but it's also kind of a weakness because you're required to do a lot in order to get anything done. There's a lot of other POMDP solvers out there that can take in, like, that don't require anywhere near as much configuration and implementation work as PomDPy does, because they just read in some configuration files type things, which you do have to understand in order for it to calculate properly. But for PomDPy, you had to do it the way we did it, you have to implement minimum 5 classes, all of which are inherent from other classes. So there's required implementation that you have to do. There's methods and things. I think the total amount of code that was written was between 800 and 1,000 lines of code, which is not a lot of code, but when you consider that just to enumerate like a handful of actions, I think there were 7 actions that were able to be taken, that was like 40 lines of code or 50 lines of code. So it's powerful, but it's not easy to set up. And there's if you want to make any changes to what you've done, that ends up being a lot of work too, because you have to touch a lot of code in a lot of different places to make fairly small changes. It's also stuck on Python 2.7 because it hasn't been in active development for a few years, which is what it is, but is maybe less than ideal now that that's at end of life. So I'm going to talk a little bit about the classes. Network state, network action, and network observation. I chose those names because the problem was the network problem. And they represent kind of the basic state, action, and observation concepts that we talked about a little earlier with like the mathematical background of POMDPs. So there's that. There's also network model and historical network data. The network model class is really the main workhorse of the implementation. It does state transitions, observation generation, reward generation. It does epoch updates if you're doing reinforcement learning. It does everything basically. And it's probably the biggest single file that I made for this, and I think it's between 400 and 500 lines of code, which makes sense. But when you consider that there are also solvers that can do that with 50 lines of configuration files, I don't know. I think it might be worth looking into alternatives for future work, but I'll talk more about that later. There's also historical network data, which is responsible for building and storing histories over time as you are generating policies with the model. It also is responsible for kind of the handling the simulation aspect of it, where as new choices are generated and as you sample from them, then you'll make a choice, and then that class will end up pruning kind of the tree of choices down to your one final answer. Like Connor talked about, we had a few different types of vulnerability, and these had to be hard-coded in, which works, but is maybe not ideal. And machines could have different combinations of vulnerabilities. It's not like each machine only had one. But again, Connor's talked about that. So in terms of operations steps, again, this is something that's already been covered. I'll run through it real quick just as a refresher. So you take a Nessus scan of your target area, your target network. You have to do the scan output conversion, which is simple Python script. You feed the result of that into PomDPy, and it does policy generation with reinforcement learning. And then you have to translate that policy so Caldera can parse it and generate an attack plan based on the results of the algorithm. So pretty straightforward. It's a pipeline straight through. In terms of results, the pipeline works. I did end up generally running this with fewer epochs than the default settings. I think the default setting is 10 epochs. I also reduced the number of simulations per epoch because hardware limitations. So it does generate policies. We had some issues at first generating policies that kind of made sense. It generally only makes legal moves now. So we seem to have squashed that. It does sometimes have issues picking like the most optimal quote unquote vulnerability, but it does not make illegal moves ever. So there's that, which is always good. But yeah, that generally takes at 5 epochs with a reduced number of simulations per epoch. It runs in about 3 to 4 minutes on my machine, which the VM, I'm allocating the same kind of VM that Connor is, 2 cores and 3 gigabytes of RAM. So it's not slow, but it's not like instant either. And scanning and policy generation are probably the slowest parts of this, which, you know, really due to hardware limitations more than anything. I do have an example of the policy that it generates. So this, you kind of have your history sequence, like I mentioned, excuse me. And so in this one, for example, it generates a scan action, and the observation it makes on that is that this node has a VNC vulnerability. And then the next action it takes is it exploits the VNC vulnerability. And that node in the network then becomes root, because as we previously discussed, our exploit actions are atomic for performance reasons. And then after that, it says, hey, this node is root, and makes a lateral move to a different node in order to continue the attack. So this is a sample. This is just so you guys can get an idea of what it's outputting. It does output in a human readable form. So yeah, some final thoughts. This isn't perfect, but I don't think perfection was ever really the goal. It works. It's a proof of concept. It shows that this is a feasible area of research. In terms of PomDPy, I think looking into other solvers is probably not a waste of time. I think it's worthwhile as kind of an avenue of improvement. I think it also would be worth looking into a Nessus alternative, even though I don't know of any. it's kind of best in class for what it does. And there's not a lot of open source software that can compete with it without some pretty major trade-offs. But it'd be worth looking into. It might also be worth looking into writing one from the ground up, which goes into kind of my recommendations for future work. While this does work, and it, you know, works pretty well, I think that building something, having a more purpose-built solution would probably be better than something kind of kit-bash like this. Something more comprehensive, something that is taking pieces that are more designed to go together and not just kind of taking things and sticking them together. I think that would be a good avenue, and trying to build maybe a full framework for this kind of thing, even if it's just, hey, now we can slot these pieces in more easily and make it more of a modular type thing. That could be another way to view that. Scalability is also another area that could be worked on, because we've been kind of held back by performance in terms of like hardware limitations. And this in particular, in the past few years, there's been a lot of like approximation work that's been done and that kind of thing, which this project in particular, PomDPy, benefits from a technique called Monte Carlo tree search, which I think has really only been popularized in kind of artificial intelligence in the last 5 to 10 years. You have things like AlphaGo, Google's Go, artificial intelligence Go playing software that beat like all the world champions of Go. It used Monte Carlo tree search and simulation in the same way that this does in order to make its decisions. It simulated however many exponential possibilities that there are in Go, and it used sampling and tree search in order to hone in on the best decision. And so I think that more approximation techniques will probably be created, or maybe older ones that have been discarded could be applied to this in other areas. Subdivision of work is also, and parallelization of work is probably another big area that you could do for this, because in that same vein of it being computationally expensive to run this simulation, if you have, say, a big server and you've got a whole bunch of VMs, it might be possible to make a kind of, not quite command and control setup, but like maybe like server client setup where you send your data to, you send your algorithm data to a whole bunch of nodes. They do the computation massively parallelized, and then they send it back to you. And that could be a way to speed it up and make this more scalable. Another thing that could be worth looking into is multiple attackers. If you have multiple agents on the same network and they're attacking different parts of it, then maybe there's some way, either via a command and control server or for just intercommunication, for them to let each other know, oh, you know, this node I've already done, you don't need to bother looking at it, and that kind of thing. So that could be some future avenues for work. Might also be worth looking into other types of algorithm, maybe ones that aren't state-based, so you kind of sidestep some of these problems entirely, but I don't know. So that's all I have in terms of slides. If there's any questions, be happy to answer them.
Yeah, one comment I could quickly jump into is like OpenVS, which is a sibling of Nessus. So you may use that as one of the scanner. So it's open source. I think my main question is regarding to the scalability, right? So because for both the scanning and also the POMDP modules, definitely need to address these state exploration issues, right? So now we only have 3 virtual machines over there. So consider if we have a large data center system, so there could be tens of thousands of virtual machines and quite a lot of vulnerabilities. So if we do these autonomous scanning services and decision making and to explore the vulnerabilities, that would be a big challenge. I think I see this kind of a special case study, right? So based on a small setup, in case if we want to measure the performance for a large system, then we need to think about we need to do kind of like emulation to assume there's a duplicate, maybe with different setup of network topology and also vulnerabilities with different combinations, and try to run the algorithms multiple times to get the statistic evaluation results to show the trend when the number of vulnerability got increased and how your entire system model works in terms of the scalability issues. So I don't know how much this work can cause you guys to do additional testing, and but I think if it's doable in a short time period, that's definitely is worth the effort. That's not just say, okay, we have a toy example, we can solve it, but we don't know how, when the system become big, become large, how we can address that. So I think that's my main question about it, or maybe suggestion for this work. Additionally, I think these other issues like when Corner present his scanning service module, and mostly we based on the known vulnerabilities, right? So you're using the system to explore the known vulnerabilities. This is quite limited in a sense. For example, like APT type of scenario, attacker may not just using tools to explore the known vulnerabilities, right? So they may do a combination of normal activity and exploration of attacks, not just within a short time period, but maybe spend out like days or maybe weeks to do this kind of explorations, right? So to emulate those kind of scenario, I think there could be some additional models we can add into Caldera. So in a sense, we can emulate some of the normal activity as well, right? So this is my two major comments, regarding to this part of work. Okay, yeah. So now let's see if others in the Zoom channel have questions. So everybody is fine with that?
Yeah, I asked the questions that I had already.
Okay. So do you have other questions? Oh, by the way, are there any quick demo or presentations in addition to these, slides both of you want to give? I think this is the opportunity for you to show.
I don't have anything set up for that.
Okay.
But yeah, I wasn't really, I just wasn't planning for that to be part of this, but.
Sure, no problem. So also, Connor, do you have anything additional stuff you want to add in there?
I got all of the kind of ThoughtLab components set up in a way. I'm not positioned at the moment to run like a live demo, but all the components are set up on thoughtlab.com for future replicability of this work.
Can you guys share your code repo and update the README so like anyone who is planning to use the system can easily replicate your solution?
I've been working on that over the past few days, so I'm working on writing some thorough kind of READMEs for each section of the code. So like going into Caldera, like here's the stuff you need to do, here's how the configurations that we use and stuff like that, how to implement that. I'm going to do something similar for Nessus. I just haven't written like the Nessus specific file yet, but that should be made public now. So you should be able to access it using the link in our paper. And it'll just be a matter of finishing out the like readmes and like Nessus for like exact configuration if it's even something that you want to include.
Okay, I think that's good. So I will send both of you my feedback through the email, maybe through the Slack channel, and see within a short time period if we can make updates of your thesis, right? So then I can inform the Barry School regarding to the your honor thesis. So let me take this opportunity for thank you both of you and hard work and good presentation, and hope this can be a stepping stone for you to move to the next step for your career. And also I'd like to thank the participants in this conversation and thesis defense, and so hope this could be useful for you. And so if you have additional comments or anything, feel free to send us a message so we can see, you know, based on this work, maybe it's useful for your current work or your future work. So we would like to build up some collaborative opportunities out there. So I think that'd be all if no one want to provide further comments or suggestions.
Yeah, I think this is a good starting work on this topic of AI-based autonomous penetration testing. So basically, idea is that there are a lot of humans involved in penetration testing, and while they are very good currently at what they do, like if you see the number of IoT devices and the attack surfaces increasing exponentially. So if we can come up with some kind of autonomous solutions that try to strike a middle ground, so like give penetration testers kind of a breathing space and help them manage this complexity of like the exponential increase in attack surface with number of devices. So that is the end goal, and we probably will keep on building on this initial work that Eric and Connor have done and try to expand it through other students who will be taking up this work as their masters or maybe doctoral thesis. And I think I would like to thank Connor and Eric for great work on this topic and selecting this for their honors thesis. And I wish them very best for their future endeavors.
Mm-hmm.
Thank you.
Yeah, thank you both so much for all the help you've given us. Really appreciate it.
Okay, thank you very much. And as I said, I'm going to send you feedback very soon, and let's see and finish this semester over this virtual conversation or works. All right, and stay at home and be safe. All right.
Thanks,
All right.
you too.
Okay.
Thank you.
Thank you, everyone.
Bye-bye.
Thank you, everyone. Let's see, I'm gonna stop the recording as well.